resonance of electrons in covalent compounds. The resonance, electron resonance, is a difficult topic to grasp. So two things I want you to think about that are going to help you think about this topic here. The first thing is that the pictures we draw are static pictures. They're really bad in this regard. And electrons are moving. They are moving fast. How fast does an electron move? If an electron could circle the Earth, it would take 18 seconds. Electrons are trucking. They're like on PCP and crystal meth, all wrapped up into cocaine. So the resonance of electrons. Let's start by drawing a Lewis dot structure of SO2. Now, by drawing a Lewis dot structure here, we have our three-step method that we are going to cycle through to get a good Lewis dot structure. Our total electron count for the sulfur and the two oxygens are sulfur is going to bring 6 valence electrons, and oxygen is also going to bring 6. So we have 6 for sulfur, and then that's 18. So we have a total of 18 valence electrons in this Lewis dot structure is all we're allowed to have as a total electron count. Let's start with our simplest prediction of making one bond in between these atoms. Everybody has one bond. Now we're going to check octets and fill them in. This oxygen is happy. This sulfur is happy. And this oxygen over here is now happy. Everybody has an octet of electrons. When we cycle back up and check this up, this has too many electrons, TWO many electrons. So I'm going to make one more bond in between these oxygen atoms here. I'm just arbitrarily placing it there. I could have put it there, but I'm just putting it here because it's closer to my hand. So now I'm going to check my octets again. This oxygen is still good. This sulfur can now lose 2, and this oxygen can lose 2. When I cycle back up a second time, so now this is a good Lewis dot structure with 18 electrons. This is a static picture of this molecule here. This picture does not show the movement of the electrons, and electrons are moving very, very fast. This is meant to be a model trying to show the electrons in bonds in this molecule. We have 2 bonds over here and a single bond over here. Doesn't show all the electrons, just the bonds right here. Now, these electrons are moving very fast. And the question I pose to you is, remember, these electrons could circle the Earth in 18 seconds. So if this electron hypothetically looks over here, it may think the grass is greener on the other side and would bounce over to that position. It is moving into an identical energy level, going from a sulfur-oxygen pi bond to a new sulfur-oxygen pi bond. What that molecule would look like is sulfur in the middle. I want to be very clear about this purple pair is supposed to be the pair that moved. I want to be clear that now we have dose bonds in between here and only a single bond in between here. And then I'm going to fill in now the moment these electrons move over and make a bond, these electrons from a lone pair are going to do a similar sort of shift to fill in octets. So now we have an octet on both sides. Here is a model trying to show, again, that double bond movement right there. I note that these are identical structures. They are mirror images of one another. Now we have to note that, remember, each of these images is a snapshot in time. It is a static image. Because the electrons are moving fast, for them to flip-flop back and forth, going into energetically equivalent positions is no consequence of the electron. It's a very, 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 very short distance, and the electrons are moving very fast. This is resonance of electrons, moving from a pi bond to make a new pi bond, and then bouncing back and forth again. And this is what we call resonance in chemistry. Thank you.